In this video here, we're going to take a look at Hooke's law and dynamics problems. So we can also use Hooke's law to solve dynamics problems involving elastic strings or springs. And it should go without saying here, but just make sure then that you've watched the previous video where we introduced Hooke's law and that you're confident with the material featured in that video. So there isn't really much to introduce here. It's just basically a follow-on from the previous video, but now just exploring dynamics problems. Okay? So let's just work through a practice question together here. So let's just get started then with the one practice question for this video. Now, as we can see here, right, there is quite a lot of waffle for this question, which can be pretty standard for further mechanics problems anyway. But if you want to, just pause the video here, have a quick read through it. I will read through it anyway, but if you'd rather go at your own pace, like I said, just feel free to pause the video. So what do we have then for this question? So what I've got here is a particle of mass 0.4 kilograms that's attached to one end of a light elastic spring of natural length 1.2 meters, and it has a modulus of elasticity of 12.5 newtons. Now the other end of the spring is attached to a fixed point O on a rough plane. So because it's on a rough plane, we know then at some point in this question we'll have to deal with friction, and this is inclined to the horizontal at an angle alpha, where tan alpha is equal to 3/4. The coefficient of friction between the particle and the plane is 0.25, and the particle is held at rest on the plane at a point which is 0.8 meters from O down a line of greatest slope of the plane. And then finally, what we're told here is that the particle is released from rest and it moves down the slope. And all we want to do then is just find its initial acceleration. Now, as we can see here straight away, we don't have a diagram for this problem. And to solve a question such as this one here, a diagram really is essential, right? Please don't attempt this question without a diagram. It's asking for trouble. So let's just begin there by drawing a quick diagram. It doesn't need to be a masterpiece, by the way. So let's just begin then by drawing the inclined plane here. So we'll get to say something like this. Clearly, this should just be a straight line, but it doesn't matter too much. We have the horizontal, like so. We've got our angle of inclination here. So that's given as alpha. What else have we got here? So we've got the particle right now. The particle here, as we're told then, is 0.8 meters from O. So O is at the top of the inclined plane here. Let's just say that this is O. And it's 0.8 meters from O. So I'm just going to put that, say, somewhere around here. Okay. So this here then is our particle. And in that case then, this distance here is, as we've just said then, 0.8 meters. Okay. Now, the particle here is attached by the light elastic spring, right? So it's attached to the fixed point O. It's going to look, say, something like this. There you go. That's my masterpiece of a spring there. You can tell that I failed out, by the way. But there we go. So that's the spring. That's O. What else do we have here? So we have a normal reaction right between the particle and the inclined plane going up here like so. So I'm just going to label that as R, like so. We've got friction here. So the particle, as we're told then, is released from rest and moves down the slope. So it's going to go down the slope here. So friction will oppose motion, right? And friction will act up the plane. So we've got F here acting up the plane like so. What else are we missing here? So basically what we're told here is the natural length of the spring is 1.2 meters. So what I've got here is a compression, right? The spring is compressed. And in that case then, what we've got here is a thrust force, right? So in that case here, the thrust force will act down the plane. So just be very, very careful for that. So the thrust force here acts down the plane, and I'll just label that as T, like so. If it's going down the plane, don't forget as well that we also have acceleration acting down the plane here. So I'll do that to the side here. As you can see, I don't have a ton of room for my diagram, but we're nearly there now. What else are we missing then? We're missing the weight force here, right? So the particle has a mass of 0.4 kilograms. So acting vertically downwards here, we have the weight force then, and that would be 0.4 G. Perfect. So I think at this point here, that's everything that we need now for our diagram. clearly what we need to do here is split the weight force into components, but I'll come back to that in just a moment. So to begin with here, let's just apply Hooke's law, right? So just make a quick point here. So by Hooke's law, here, what do we have then? So we know by Hooke's law here that T is equal to lambda times X over L. So lambda here is the modulus of elasticity. X, in this case here, so again, just be very, very careful. X isn't the extension. X here is the compression, right? The spring is compressed. So X is the compression in the context of this question. And L here just represents the natural length of the elastic spring here, okay? So if we put this all together then, what we get here is lambda, which is 12.5. We've got 12.5 times by X. So what is the compression here? Well, the natural length is 1.2 meters. This distance here from the particle to the fixed point O is 0.8 meters. So the compression then is 0.4 meters, right? We times that by 0.4, and we now divide then by the natural length, right? But the natural length here, as we're told in the question, is 1.2. Perfect. And just evaluate this here then, so just use your calculator, right? And if you do this correctly then, what we get here in exact form is 25 over 6 newtons. Okay? Perfect. What we're now going to do is resolve here. So let's just begin by resolving perpendicular to the plane. Okay? So if we resolve perpendicular to the plane here, taking up perpendicular to the plane as positive, like we said before, I do need to split this force here into components. So I'll do it in a different color just so you can see it a little bit easier. Let's just do it in red then. I don't have tons of room as well, so it's not going to be the easiest to see here. Like so. That's a right angle triangle. So going down here, so perpendicular down, or going down in a perpendicular direction. There we go. English is hard. What we get here then is 0.4g cos alpha. So this would be 0.4g cos alpha. So 0.4g cos alpha. And then this component here, you might have guessed it, that would be 0.4g sine alpha. Okay, but this should hopefully be pretty straightforward, right? Just splitting this force into components here, we obtain the following. Okay. Now, if we resolve perpendicular to the plane here, just going back to my original pen color then, what do we get here? Now, we don't have any acceleration perpendicular to the plane, so it becomes quite straightforward, right? In this case here, r, so r is positive because it's going up here, perpendicular to the plane, is equal to this component here, right? This component here is acting down, perpendicular to the plane, and that's 0.4g cos alpha. Okay, so r is equal to 0.4g cos alpha. Okay. Now, what else do we know here? Well, because we're told that tan alpha is equal to 3 over 4, what we've got here is just one of our Pythagorean triples, right? 3, 4, 5 triangle. So in that case, then what I get here for cos alpha, so if tan alpha is 3 over 4, what that means then is we have sine alpha and cos alpha. I don't have tons of room. I'll just do it underneath here. So cos alpha here, that would be 4 over 5. And then sine alpha here, that would be 3 over 5, right? Perfect. So in that case, then what I've got here is that r is equal to 0.4 times 9.8, because that's g, right? So times by 9.8 times by cos alpha, which is 4 over 5. Perfect. All we need to do here then is just put all of this into our calculator. And if we do this correctly, then what we get here for r is 3.136 newtons there. Perfect. Now, what we're told here is that the particle is released from rest and it moves down the slope. So in this case, F is equal to mu r because the particle is about to move, right? So make another point here. particle. The particle is about to move. The particle is about to move. In that case, then, F here is equal to mu times R. So in that case, then F here is equal to mu. So mu then, don't forget, it's just the coefficient of friction here, which as we're told in the question is 0.25. So I've got 0.25 times by R. Well, we've just evaluated R, right? R is 3.136. So 3.136 there. Again, just put this into your calculator. And if you do this correctly, then what we find here is that F is 0.784 newtons there. Okay, perfect. So we're nearly there now. What we now need to do here is just resolve parallel to the plane, right? So now let's resolve parallel to the plane. So we've resolved down the plane here, like so. I'll take it down as positive then, parallel to the plane. What do we get here? So I've got two forces that are acting down the plane here. I've got this 0.4 G sine alpha, that's this component here. And we also have the thrust force, right? So let's just put that together then. We've got 0.4 G sine alpha. So that's this component here. We also have the thrust force. The thrust force acts down the plane, parallel to the plane, of course. So plus T. Now we do need to account for acceleration here. It does accelerate down the plane, so we will need to take that into account. Going in the opposite direction now, we have friction, right? So minus F here, like so. And this is equal to the mass times the acceleration. So the mass here is 0.4 times by the acceleration, which we don't know what it is, right? That's what we're looking to solve for here. So 0.4 A. Perfect. Okay. So again, let's just substitute in as appropriate here, right? We know what sine alpha is. That's 3/5. We know what T is. We evaluate that here. We know what F is. We've just evaluated that here. So we've got everything that we need now, right? So I've got 0.4 times 9.8 times sine alpha, which is 3/5. So what I'll do here then is just put all of this inside a bracket, like so. We've got plus T here. So what is T then? That was 25/6, right? So plus 25/6, like so. Minus F then. So what is F here? So F is 0.784. So minus 0.784. Perfect. And all of this here then is equal to 0.4 A. So at this point here, just use the calculator, right? Just put all of this in here on the left-hand side, divide it by 0.4. And if you do this correctly then, this just gives us A here. And in that case, then what we get here for A is 14.33, so on and so on. And if we just round this then, so let's just say two significant figures here. What that tells us then is that the initial acceleration, I'll just write this down in full, by the way. So the initial acceleration is, so what do we get then? 14 meters per second squared. So 14 ms to the minus 2 there. Perfect. And there we have it then. So like you can see, there is quite a bit of work involved with questions like this, but the most important thing here is that you do draw a diagram if you're not given one in the question. So please don't try and attempt a question like this without a diagram. It's never going to end well, right? So just draw the diagram. But there we have it then. So like you can see, hopefully not too challenging. If there's anything that you're not too sure about, as always, just leave a comment and I will try my best to help. But there we have it then. So that gives us the solution here to the one practice question for this video. And that brings us to the end then of this video here on Hooke's law and dynamics problems.